So, welcome back to this advanced manufacturing and process modeling course. So, till the last class we have discussed about the basics of casting solidification, and also we have discussed how to design the gating arrangement for achieving cast parts with sound structural integrity and mechanical properties, and also how to achieve the desired dimensional attributes in the cast part. And so now we will move ahead with the casting processes. So we will discuss about different casting techniques, but before that, first of all, for metal casting we need to prepare the melt. So how to prepare the melt? So we need to prepare the melt using a resistance heating furnace or using a induction heating furnace. So the basic principle is basically to heat the ingots and to prepare liquid melt out of it. So that means the heat which is going to prepare the liquid melt, we can split it up in three components. So number one is the heat required to raise the temperature of the solid ingot from ambient temperature to the melting temperature of that particular metal is concerned, and then there is a heat of fusion which is needed for the phase change process. That means solid to liquid. So that is the HF over here it is shown. P rho V HF, and then where V is the volume of the metal used for heating and rho is its density of the ingots that are used, and then Tm is the melting temperature, Ta is the ambient temperature, and so we are talking about this equation. So here you can see this is we are estimating the total heat input required to for melt preparation. So after the supplying of the latent heat, then the additional temperature hike of the liquid melt to raise it to the superheated condition to the desired pouring temperature, because why we need to raise the superheat beyond the melting temperature of the particular metal or alloy is concerned, because we also want the liquid melt to flow through the gating arrangement, right, that we have discussed in earlier classes. So so we have to provide enough superheat to the melt so that it remains flowable. We have also discussed about the concept of fluidity. So to provide enough fluidity to the liquid melt, we need to raise the temperature a bit higher. That also depends on case to case basis. We will while progressing with this class today, we will also discuss about the low superheat casting and semi solid casting. So there you will understand that how we will play with the melt pouring temperature to achieve the desired quality characteristics, that means the desired properties and the microstructure in the cast part. So moving ahead, so the assumptions valid for the equation which is shown in the previous slide is the specific heat and other thermal properties of a solid metal are constant and not dependent on temperature, but that is not actually true, especially if the metal undergoes a phase change process during heating. Number 2 is sometimes specific heat of metal in solid and liquid states are assumed to be same, but that is not really the case. Number 3 is single melting point, which is not valid for alloys because there is a temperature range between the liquidus and solidus temperature of the particular alloy. That means the melting starts at the moment the temperature overshoots the solidus temperature of that particular alloy, and the melting becomes complete only if the temperature overshoots the liquidus temperature of that particular alloy. And number 4 is there are no heat losses to the environment during heating, which is also very much not true. Only if we are doing the melting operation under vacuum, then it can be achieved, but otherwise there is some amount of heat loss. So these are the assumptions considered in the equation which is shown in the previous slide. So now we have to estimate the pouring time. We have also discussed about the filling time earlier. So the primary goal in getting system design is to minimize the pouring time so that we can fill the mold in a minimum possible time frames, which is essential for mold filling. Pouring time depends on factors like material, casting complexity, section thickness and size. So steels which loses heat quickly require shorter pouring times, while non-ferrous metals benefit from longer pouring times to avoid avoid dross formation and account for slower heat loss. So why I mean this non-ferrous metals need longer pouring time, because please recall that we have discussed about non-pressurized getting system in case of non-ferrous metals, because we basically want the melt to be filled within the mold in a laminar manner, and that laminar manner can be achieved because there is no back pressure involved in the getting arrangement in case of non-ferrous metals. So that is why understandably the pouring time is larger, higher in case of non-ferrous metals, so which is analogous to achieve laminar melt flow within the mold cavity. So, so here there are some following are some standard methods to calculate the pouring time for different casting materials. So, for example, grey cast iron for mass lesser than 450 kg, the empirical formula to estimate the pouring time is depicted here, which is equal to K 1.41 into 1.41 plus T by 14.59 into W to the power half, where W is the mass of the casting, T is the average section thickness, capital T, and capital K is the fluidity of iron in inches divided by 40. So, and similarly, when the same material, that is the grey cast iron, the mass is greater than 450 kg, mass of the casting of course, then the empirical formula to estimate the pouring time changes and it takes the following form. So, so these are some empirical relations that has been developed for industrial practice, so that it can be estimated the pouring time in a shorter span of time, and also accordingly the other process conditions and the getting geometry, and also this will be helpful to predict the microstructure and the cooling rate that the solidifying melt will be subjected to. So, all these estimations can be done based on the estimations of the pouring time. So, moving ahead, so these are some typical pouring times for cast iron is given for different casting masses, and also for steel castings the empirical relationship for pouring time estimation is given. For copper alloy castings the pouring time estimation empirical formula is also mentioned over here, and also in case of different processes, for example, for the same steel castings, when in spite of sand molding we are going to the cell molded condition, or in case of ductile iron, so then also the pouring time changes. So, you can understand for the same material and same process, when the casting size changes, we of course there is a change in pouring temperature, and also for the same material, when we talk about same volume of the casting, same weight of the casting, however we are using different processes altogether, then also the pouring time changes. And also pouring time is largely depends on the pouring temperature, because when we are having higher pouring temperature, that means the the gap between this is, if this is the equilibrium melting temperature, then this is the superheat temperature. So, I can term it as Ts, T superheat, and Tm I am talking about in case of pure metals. So, as the degree of the superheat increases, the fluidity also increases accordingly. So, this is say fluidity, and this is fluidity, and this is the degree of superheat. So, as the superheat increases, fluidity increases, and also that in turn decreases the pouring time. Okay. So, there are several factors which plays their role, and the pouring time of the casting is basically the combined effect of all those parameters. Complex interplay of the various process conditions determines the pouring time of for the metal, for the particular casting on case to case basis. Okay. So, there are some other pouring time formulas given here in case of intricately shaped thin walled castings of mass up to 450 kg, for castings above 450 kg and up to 1000 kg. So, typical pouring times for casting whose mass is less than 200 kg and average section thickness of 25 mm are for different material it is listed. For grey cast iron it is around 40 seconds, for steel it is around 20 seconds, and for brass it is between 15 to 45 seconds. So, so you can in continuation of my previous statement that the pouring time varies across different processes for same material, and for same process or same size of the casting, weight of the casting, it varies across different material which is undergoing the solidification process. So, this is how it varies. So, now we will discuss about the different variants of casting processes. So, casting can be largely classified as expandable mold based processes, permanent mold based processes, and continuous mold based processes. So, expandable mold based processes can be further classified as sand casting, cell casting, investment casting, full molding, and CO2 molding. Whereas permanent mold based processes can be further classified as centrifugal casting, die casting, slush casting, and squeeze casting, wherein die casting can be further classified, which are also one of the most widely used industrially used practices, like gravity die casting and pressure die casting. So, we will also talk about how we can do semi solid pressure die casting later on in this class. So, but for now, pressure die casting in general can be broadly classified as hot pressure die casting and cold pressure die casting. So, this hot and cold is basically in terms of the chamber casting chamber temperature. We classify both the processes as hot or cold chamber pressure die casting process, and whereas centrifugal casting also can be subdivided as true centrifugal, semi centrifugal, and also centrifuging. So, they are also with this variation of why they are having different nomenclature, because they also decides the what are so this classification is made based on the different kind of castings can be produced by individual techniques. So, and the third variant, the major variant of the casting processes is termed as continuous mold. So, we will come to that later. So, we will start with sand casting, but sand casting we have already discussed in the former last class in detail. We have also discussed about several functional parts of the gating arrangement. So, which is also shown again here for your ease of understanding, and we have also discussed about the steps involved in case of sand casting. So, why you can see it is like a recap for you. So, here you can see the pouring basin, then you can see the tapered sprue, then the sprue base well, which is also called choke, then there is runner, then there is ingate. So, this is basically the ingate, and then this is basically the open riser, which is having same height to that of the pouring basin or sprue, almost the same height. So, where from the sprue starts, and you also can be seen the sand core. As please recall that I have told earlier that core sand is slightly of improved quality than the sand utilized for the sand mold making, and also we use specific type of binders to bind the core sand, so that we can get the desired core geometry, and accordingly the corresponding hollow shapes can be made within the cast parts after solidification. Okay. So, and we have also discussed about the several steps involved in case of sand casting process, like first allowing the melt to flow within the die cavity, then allowing it to solidify, and then once it is perfectly solidified, then we do the fettling process to remove the gating arrangement to get the final desired cast geometry. Okay. So, then we will move to the shell casting. So, shell casting yields better surface quality and tolerances. The process is described as follows. So, the two piece pattern is made of metal, that is aluminum or steel, and it is heated to between 175 to 370 degree centigrade and coated with a lubricant, that is silicon spray. So, here you can see in the schematic the pattern is shown over here, and this is basically the shell, the dump box, and then so then each heated half pattern is covered with a mixture of sand and a thermoset resin or epoxy binder. The binder glues a layer of sand to the pattern, forming a shell. The process may be repeated to get a thicker shell. So, the assembly is baked to cure it, and then we use that shell to to develop the cast part. So, this is how we do the shell casting. So, next we will discuss about investment casting. Investment casting is also quite similar to the shell casting, but there are certain differences that we will explain. So, the major advantage in shell casting is that we can really manufacture some complicated geometry parts by shell casting, and also we can achieve much higher surface finish in case of cell cast parts compared to what we can achieve in case of same parts being made by a sand casting route. Okay. So, here you can see the sequential process of the shell casting process, that is what is shown over here, and then finally molding the melt into the shell prepared and to cast the part. So, here comes the investment casting. So, investment casting is a typical example where we can go, which technique we can adapt when there is high accuracy and precision of the cast parts are on demand. So, why we can achieve that? So, basically how we do the ceramic cell preparation. So, here we use ceramic cell as the mold where we can basically we fill the liquid melt, and thereby we achieve the solidified geometry or desired part geometry. So, what we do initially, we do the wax injection. So, this is very much similar to the injection molding process that we will discuss subsequently when we will discuss about the powder metallurgy module of this course. So, after injecting the individual, so you can see this is a basically a multi cavity mold that we are preparing. So, we are getting a number of components from this single tree mold cavity. So, we are basically doing the wax injection and making the individual wax pattern of the individual components that we are going to produce, and then we annex them in the form of a tree. So, these are basically wax injected wax replica, wax patterns you can say, and then we arrange these waxes around a central sprue. This is the central sprue basically, and then when the tree is made which is made of wax, we basically dip it simultaneously or number of times within a ceramic slurry, and then that slurry gets so that wax tree gets a coating of the ceramic slurry, and that slurry gets thickened, and thereby the ceramic shell is made. And once that ceramic shell is ready, then we basically heat it up so that it can get baked, and also in the heating process the wax gets melted, and then we can just invertly place it. So, because of the inverted position, the wax drains off, and then we use the same shell for melt pouring, and from there we can get the cast multi cavity cast component in a tree shape, and then we basically cut them off so that we can get individual components. So, this is how the investment casting is performed, and investment casting as a widespread application in directional solidification, and also in case of single crystal castings of high temperature turbine blades that we will be discussing later on. So, investment casting, the first step is to produce a pattern. So, I have already discussed about the steps. So, these steps are listed over here. So, after producing the pattern, we basically the prototype, small production runs and specifically projects can also be undertaken by carving wax models, and cores are typically unnecessary, but can be used for complex internal structures even in case of investment casting. So, rapid prototyping techniques have been developed to produce expandable patterns. So, we can also employ rapid prototyping or 3D printing routes to develop these wax based patterns. So, in spite of making them by injection molding. So, what benefit does it gives? So, if we develop this wax based pattern or polymeric patterns by polymer this polymeric AM or additive manufacturing or 3D printing route, then we can really develop some complex contoured patterns of the components which are further going to be produced via investment casting route. And if we can produce the patterns by this AM route, then it can save us a lot of time to make the complex contoured injection molds to get this polymeric patterns made. So, thereby it can save a lot of time and also to some extent cost. However, it is only useful when we are having only a selected number of parts. That means, it is a suitable technique to develop these patterns by additive route when the batch production is involved, and when there is mass production is involved, then it is always better or advisable to go to the injection molding route, polymer injection molding route to achieve this patterns made. So I mean, so and however, we need to understand that there are some complex contoured shapes that cannot be manufactured by injection molding, or even if it is possible, it becomes extremely difficult to manufacture the tool itself, like in case of some micro features that are present in the pattern, which we need to have a replica in the form of the cast object. So there we can basically utilize the 3D printing technique to achieve this polymeric patterns and subsequent investment casting. So several replicas are often attached to a gating system, like I have shown in the previous slide. So you can see the several patterns are attached to the single sprue system to make a complete tree assembly, and that tree is basically we are dipping into the ceramic slurry, and we are getting the ceramic shell out of it. So this is how investment casting is made. These are the functional parts. And the advantages are parts of great complexity and intricacy can be cast, which are otherwise extremely difficult or impossible to be manufactured by other casting routes. Close dimensional control and good surface finish can be achieved, and works can usually be recovered for use. So that is also a important thing. So it is basically a environmentally benign process, where we need not to throw the works out, rather we can utilize the works as a pattern material for subsequent castings as well. And additional machining is not normally required, because in investment casting we basically achieve the parts in near net shape. So there is no need for further post finishing processes. And the disadvantages, there are of course some certain disadvantages like every other process. So the disadvantages are many processing steps are required. Yeah, this is true, because I only explained to you that first we need to make the pattern of the complex contour geometry of the cast part that we going to build. So that pattern first need to be built by injection molding or by 3D printing route, and then there is it is dipping it into the ceramic slurry, then making the ceramic tree, baking it, removing the wax, and then pouring the melt, and then again cutting the individual parts apart from the tree. So there are several steps involved in this investment casting process. However, they are viable only when there is very high precision is on demand. Otherwise, there are techniques like pressure die casting which can utilize which can manufacture these parts with which doesn't have that much dimensional criticality with a much lesser time, and also the casting yield can be significantly improved in that case. So so that's why, because it takes a lot of steps and time, so of course it is it is an expensive process, but the cost is justified when we talk about developing aerospace engine components like turbine blades. So where the precision and the integrity is on demand, even much more important than the cost itself. So the applications are steels, stainless steels, high temperature alloys like Inconel, IN718, CMS Export. So all these high temperature super alloys can be cast using this investment casting route. An example of parts are like machine parts, turbine blades, components for turbine engines, jewelry, dental fixtures, etc. Okay, so once we are done now with the investment casting route, we will go to another precision manufacturing casting route, which is called full molding casting. So what is actually the full molding casting? So assume that you have to cast a sphere. So then in that case, so it will be very difficult. So if we have to make a pattern, if we have to split it into two halves, that means scope and drag. So even then there will be a there can be chances of mismatch in the parting line, and if it is even becomes difficult, if you have to make a hollow sphere, or there will be an annular part in it. So because that will be very difficult by normal conventional route of castings that we have discussed so far. So that's so what is the remedy? The remedy is basically this full molding casting, where we can prepare the so pattern is basically produced by the plastic material. Gating elements will be added on the pattern itself. So up to that, it is quite similar with the I mean investment casting process. I mean that means that creating polymeric patterns and then fixing it to the tree, and then by adding slurry coatings, molding sand will be added I mean around the pattern to produce a shell. So, it will be provided inside the mold by supporting backing sand. So, so then there is also I mean we make a shell by sprinkling I mean ceramic slurry coating, and thereafter the I mean backing sand, and then thereafter we use the molding sand, so that we can get very improved surface finish around the polymeric pattern that is placed within the mold cavity, so that we can end up getting very high surface finish in the cast part itself once it is solidified. So, and then but I mean in this case what we are doing in other occasions, like we are basically removing the pattern once the I mean the mold is ready mold, but here in this case, because we are not even separating the flasks in the form of cope or drag flask, you can see here. So, it is being done in a single flask arrangement. So, because this there are certain parts where the pattern removal is become very difficult, like for example, we have discussed about several allowances, right. So, if you need to remove this pattern from the sand mold, you can understand that it will basically I mean create a hole this big, and we will never be able to achieve this kind of complex contoured shape, because the pattern is not ejectable. So, we are basically I mean following the route of fusing that polymeric I mean pattern that we are using. So, once the mold is ready, we are basically pouring the liquid melt I mean which is of much higher temperature than the polymer can withstand. So, basically the polymeric pattern gets sublimated and it gets evaporated through the porous networks that is available within the sand grains in the molding sand, and so in the form of vapor or evaporated gases, it escapes from the mold cavity and it creates the hollow cavity where the liquid metal flows in and solidifies, and then we can achieve the complex contoured shape of the casting. So, it can be used for complex shapes, cost of the process is less and generally used for low melting point materials. So, this is the full molding casting. And then the CO2 molding casting. So, to increase the strength and hardness of the large size mold and core, so I mean this technique can be used. So, CO2 molding is basically a special variant of the sand casting process, where I mean we are basically, so the mechanism is shown schematically over here. So, you can see that I mean we are using basically carbon dioxide to increase the I mean green strength of the sand mold. So, which helps in many way, like if we are trying to develop a large casting and a complex contoured casting by sand casting route, then it when you are using CO2 molding technique, then it eradicates the chances of mold swelling and also the chances of dropping of the sand within the mold cavity, which can cause sand inclusion within the metal melt during solidification, and also it can significantly cause I mean surface defects and I mean a lack of dimensional tolerance. So, that can be I mean all these difficulties can be dealt with when we are dealing with CO2 molding. So, in this case mold is prepared by adding sodium silicate binder with the sand. By creating some holes inside the mold, carbon dioxide gas is supplied. So, you can see the carbon dioxide gas supplying mechanism in this schematic, and then so it will react with sodium silicate and produce silica gel within the mold, which is having excellent bonding properties. So, due to this strength and hardness of the mold can be increased significantly, and the strength of the mold will depend on the time of supplying carbon dioxide gas to the mold, known as CO2 gassing time. So, it is generally used for preparing large size molds like machine tool beds, road roller, etc. So, this is how CO2 molding is done, and it is their versatility. So, going ahead, we now reach to centrifugal casting. So, centrifugal casting, from the name itself you can understand that we are talking about the centrifugal force that is being exerted over the liquid metal in the process of its solidification, and the resulting casting process we name as centrifugal casting. So, this is a process where the mold is rotated rapidly about its central axis as the metal is poured into it. Because of the centrifugal force, a continuous pressure is acting on the metal when it solidifies. So, the slag, oxides and other inclusions being lighter gets separated from the melt and segregates towards the center. So, we get a very improved quality of melt which is getting positioned toward the mold wall because of the centrifugal action, centrifugal force, and we also get much improved mechanical properties in the centrifugal cast parts than we get in normal sand cast parts. And the major benefit that can be achieved in case of centrifugal casting, that we can very well achieve the hollow shapes, like most of the capable process is out of these three variants of centrifugal casting, such as true centrifugal casting, semi centrifugal casting and centrifuging. It is the true centrifugal casting which is basically useful to develop hollow pipes. So, for example, if you recall, I have discussed about this hollow ductile iron pipes that are being developed in the country by Tata Metaliks, which are being developed by centrifugal casting, true centrifugal casting. So, which are otherwise very expensive if we need to manufacture them by conventional sand casting route, and then we have to machine the we have to boring process we need to do to get the concentric hole at the center. So, which can otherwise be directly achieved in near net shape by the virtue of true centrifugal casting. So, then so we will go into the true centrifugal casting. So, this is normally used for the making of hollow pipes, tubes, hollow bushes, etc., which are axisymmetric with a concentric hole. Since the metal is always pushed outward because of the centrifugal force, so no core needs to be used for making the concentric hole. That is another big achievement and advantage of this process, because you already know, because I discussed about there are some number of challenges about positioning the core within the mold cavity in a defined way, without causing any dislodging, without causing any dimensional tolerance the deficiency in the cast part. So, all those difficulties associated with the keeping a core to create a hollow section in the cast component can be totally nullified when it is possible to manufacture them by true centrifugal casting, where there is through holes are involved. So, the axis, in this case the axis of rotation can be horizontal, vertical or at any angle in between. So, very long pipes are normally can be cast with horizontal axis, whereas short pieces are more conveniently cast with a vertical axis. Okay. And then we will discuss about the semi centrifugal casting. So, how they are different from true centrifugal casting is that semi centrifugal casting is used for jobs which are more complicated than those possible in true centrifugal casting, but are axisymmetric in nature. It is not necessary that these should have a central hole which is to be obtained with the help of a core. So, again you can see that in case of semi centrifugal casting, we are bringing the core back. That means we are taking the help of the core to create the hollow. The molds made of sand or metal are rotated about a vertical axis, and the metal enters the mold through the central pouring basin. So, likewise it is shown over here. So, this is basically the pouring basin where the melt is poured, and this is the core, central core, that is kept to achieve the hollow that is needed within the cast part. And for large production rates, the molds can be stacked one over the other. That means, in that way we can produce multiple castings with one cycle of melt preparation, that is also can be achieved. And for larger so the rotating speeds used in this process are not as high as in the case of true centrifugal casting. So, basically what we are doing, we are basically taking the advantage of the centrifugal force that is being exerted over the liquid melt, and that is why we can achieve much improved grain structure with fine grained morphology, and also with the improved mechanical properties in the centrifugal cast parts. So, however, it is not a true hollow pipe or kind of a shape, or bush kind of a shape that is suitable to be developed via true centrifugal casting. So, this is basically the variant of the centrifugal casting, and the examples are pulleys, wheels and spoked wheels, etc., that can be manufactured by semi centrifugal casting. So, so then the third variant of the centrifugal casting process is called centrifuging. So, you can see from the schematic itself that we can place number of similar or dissimilar parts in a in the periphery in a circular fashion using a central sprue at the middle, and so here we can obtain higher metal pressures during solidification when casting shapes are not asymmetrical. The centrifuging process is used. So, this is suitable only for small jobs of any shape. Several such small jobs are joined together by means of radial runners. So, these runners are basically called as radial runners. So, with a central sprue on a revolving table, the jobs are uniformly placed on the table around the periphery, so that their masses are properly balanced. So, the process is like semi centrifugal casting. The only difference is, in this case we can cast multiple parts at once, and also it is not absolutely necessary that all the parts should be of similar dimension. So, again in case of centrifuging, we like semi centrifugal casting, we are basically taking advantage of the centrifugal force that is being exerted over the liquid melt to achieve the desired set of properties, and also to achieve the desired mechanical properties in the cast part. And of course, this process is suitable for a for batch production of some complex contoured components, and it is not suitable for mass production, for which we need to go to the sand or die casting based processes. So, out of that, sand casting we have already discussed, and we will be discussing about die casting next. So, like I told you earlier, that die casting can be classified further as gravity and pressure die casting. So, and pressure die casting again can be classified based on chamber temperature as hot and cold chamber die casting, wherein cold chamber die casting can be further subdivided as high pressure die casting and low pressure die casting, whereas hot chamber die casting can be classified as based on the location of the plunger or the injection unit. So, it can be classified as submerged plunger type hot chamber die casting, and also as gooseneck or air injection type hot chamber die casting. So, with this we are finishing this class, and in the next class we will go into the details of the high pressure die casting technique, and also we will discuss about the present trends of high pressure die casting processes and the latest innovations in the field, which can make a remarkable improvement in the properties and also in the microstructure of the several industries components that it can impact, starting from automotive which ends at aerospace applications. So, so bye for now, and we will meet again in the next class. Thank you.